I'm gonna start the recording now. Hello. Um, Welcome to Thursday of the second week. Almost done with week two. This is great. We're making progress. Um, the yes, okay, course announcements. Uh, I don't think there's much to say. Yeah, 25%, almost 25%. 25% tomorrow. Um, as a reminder, the first problem set is due tomorrow by 11:59 p.m. You can use your late days if you want on that. You don't have to like let me know that you're using late days or whatever. We'll just automatically like, or my TAs will do all of that accounting for me, so I don't have to worry about it. But like, we will make sure that that gets handled appropriately. Um, but yeah, it is due 11:59 p.m. I am putting the finishing touches on problem set two, which I will most likely be ready to release by tomorrow morning. If not like later tonight or something like that. So just so you know, there's going to be like a few hours of overlap between the end of problem set one and the start of problem set two. Um, Looking over it, I just realized that the second P set is going to be kind of a big one. So I would highly encourage you to get started on it as soon as possible. Although that doesn't mean anything yet because you don't have it yet. But I don't know, maybe I should save that for tomorrow morning. Um, cool. Yeah, and then of course, the project, the programming assignment. I see a handful more submissions. Seems like people are doing pretty well on that. I don't think I've seen too many like resubmissions. It seems like pretty much everyone gets most of the points in the first on their like first or second try. So that's good. Um, of course, there's office hours, there's Piazza, and you can feel free to email me if you have questions as well. Um, so yeah, cool, great. Any any outstanding questions about course logistics stuff or about assignments or anything like that before we jump into content? All right, if there's nothing, then I guess we can get started. So yesterday we went over the master theorem in a bit more detail, and kind of talked about or like worked through some examples and stuff. Um, Hopefully people understand that a little bit better now. There, like I said, there is going to be like practice problems on the problem set for you to yeah, I don't know, practice applying the master theorem, practice figuring out where and when it doesn't apply and stuff like that. Um, so I figured we could kind of move on from that. Um, Today I want to talk about dynamic programming. I know I kind of started talking about dynamic programming towards the end of yesterday, uh, and then just didn't have time to actually get through more than like a slide. So I'm going to pretend that didn't happen, and I'm going to restart that particular lecture. Uh, and so I hope that's okay with everyone. Um, let's let's jump into it. Okay. I assume people can see my screen. I say this every time, but as always, feel free to like shout out or post in the chat or something. Just interrupt me if I say something and you have questions about it, or if I don't say something and you have questions about it, or whatever. Like, feel free to interrupt me at any point. Um, I also do want this to be kind of interactive. Uh, we are hopefully going to do some live coding as well. So look forward to that. All right. Okay. Dynamic programming. So as we kind of talked about last week, uh, um, it's not dynamic programming isn't like a particular algorithm that you can use to solve a particular problem. It's like a way of thinking about problems, or it's a way of like designing algorithms to solve certain classes of problems. Um, and it is in fact a very, very deep topic. And so this one lecture is probably not going to do it justice, but hopefully it gives you like the intuition that you need to sort of go out in the world and start using dynamic programming to solve your own problems, insofar as you have problems that's applicable to. I don't know. Um, Okay, so yeah, most of the time, or a lot of the time, we'll see dynamic programming applied to things like optimization problems. So this is you have like some space of possible solutions, and the size of the space is usually parameterized by your input size. So it might be like for an input size of n, you might have a space of like 2 to the n possible solutions, or n squared possible solutions, or something like that. And the goal is to find an element in the solution space that maximizes or minimizes some objective function, right? So our maximal subarray problem from the past couple of lectures is an example of this, right? We have for an input size of n, for like an input size, like for an array of size n, there's something like O of n squared possible subsequences that we can look at. And so this is like our space of possible solutions. Our objective function says, given a subsequence, um, how big can we make the sum of all of the terms in that subsequence? And so we want to find an element in that solution space that maximizes that objective function, right? So we want to find the subsequence in the array that is maximal with respect to the sum. Right, okay. This is the idea of optimization problems. Turns out a lot of things that you want to deal with in real life, or I mean, in software engineering, as much as that is real life, I guess, I don't know. A lot of things can be framed as some sort of optimization problem, right? So knowing how to solve these can get you pretty far, I guess, is what I want to say here. So the first technique we sort of learned about is this like divide and conquer approach, right? So given some problem, some input, we break it down into like self-similar subproblems and then try to solve each of those subproblems, and we keep breaking it down until we hit some sort of base case that we know how to trivially solve. To apply a divide and conquer approach to an optimization problem, we need this sort of like we need optimal substructures, right? So we need to be sure that if we break the problem down into smaller pieces and optimize each smaller piece, that we can then combine those optimal solutions into an optimal solution for the full problem, right? So, for example, for a maximal subarray, right? If we break the array into two pieces, and we know that something is maximal on the left side, and we know something is maximal on the right side, then whatever is maximal for the whole array is either going to be the thing on the left or the thing on the right, or we have this extra case of the thing in the middle, right? But we can sort of given a maximal array for the whole thing, it sort of like induces maximal arrays on the sub problems as we break them down. And so we have this like optimal substructure. And so we know that we can kind of break the problem set down and or like break the problem size down into these smaller subproblems and kind of optimize each thing separately. So it's important to know that that's possible, or it's important to know before trying to apply a divide and conquer approach or trying to apply like a dynamic programming approach. It's important to know that applying that approach will actually give you the right answer for your particular problem. And so the general strategy here for divide and conquer is you take your big problem, break it into subproblems, optimize each subproblem, and then combine all of those optimal solutions in some problem specific way. So hopefully a lot of this is a review. It turns out dynamic programming is just divide and conquer plus a little bit of extra work to make it more efficient, right? Dynamic programming is just like an optimization that you can put on top of a divide and conquer algorithm. Or it often suffices to think of it that way, right? So why do we need an optimization? Well, the trouble with divide and conquer algorithms is often if you split something into if you split an input of size n into alpha smaller subproblems, each of size n minus k, the recurrence relation you get looks like that. T of n equals alpha times T of n minus k. Um, and if you solve that recurrence relation, you get something that is, you get a complexity that's exponential, right? And we don't like exponential complexity because that like doesn't scale very well, right? Um, okay, so oftentimes our naive approach will give us something exponential and we want to be able to fix it. When can we fix it? Well, if the space of possible solutions is not exponential, then uh, there's a good chance that our recursive algorithm, which is like visiting an exponential number of solutions, is visiting the same solution over and over again, right? And so we can sort of um, avoid doing all of this extra work uh, to to compute our final answer. And so we can kind of right, we can like cache the results, or we can like do some more clever strategy to like figure it all out. For example, if you remember from our Fibonacci problem, or from our like Fibonacci algorithm from however long ago that was, the recursive function takes like Fibonacci of n is fib of n minus 1 plus fib of n minus 2. And so this visits an exponential number of things, right? It visits like roughly 2 to the n. It makes like roughly 2 to the n calls to this function. But if you think about it, there's only n different Fibonacci numbers, right? So there's way fewer than the 2 to the n calls we're making. And so we know for a fact that we're calling the same function on the same inputs multiple times over and over again. And so we know that we can do something to like fix this, right? So that's the idea. Um, Now, I want to do this in the context of a running example that I'm going to use, which is called rod cutting. This example is taken from the textbook, Intro to Algorithms. Um, as I mentioned before, there's a reference to it in the syllabus. It's a great book. It's kind of big. You probably don't need all of it, but if you want to read more about dynamic programming, it's a pretty good reference, I think. Um, okay, so the rod cutting problem. It turns out that the amount that someone was willing to pay for a length of rod is often not proportional to the length, right? So for example, you might have um, we might have a pricing model that says like 1 foot, 1 unit of length or whatever is $1, 2 feet is $5, 3 feet is $8, and 4 feet is $9, right? So this is not proportional. Like different, the incremental extra amount that you pay for each additional foot like changes somehow, right? And so if we have a 4 foot rod and we're allowed to like break it into integer pieces, we can sell it all at once for 9, right? 4 feet is $9. Or we can break it into 4 1 foot rods, sell each one for $1, and that's a total of $4. Or we can sell it as 2 2 foot rods for $10, or we can break it into a 3 and a 1, or a 1 and a 3 and sell it for 8 plus 1 is 9, right? So the point is, the way we break this 4 foot chunk of rod down, the way we choose to break it down matters in terms of how much money we can get for it, right? And in this case, the optimal answer ends up being break it into 2 2 foot pieces for $10 because we've sort of enumerated every possible thing. Right, so that's the optimal solution. But how do we know that that solution is optimal? That's sort of what the rod cutting problem asks. Is it's like given a table of prices, given like an array or something, right? That tells you how much someone is willing to pay for um, any integer length of rod, and given some initial like length, how do you or what's the maximum amount of money that you can get by like breaking it down into sub pieces or whatever? Uh, okay, so that's the problem. Now, if we just try to brute force this, right? Like for the case of n equals 4, right? For a 4 foot rod, it turns out there's like not that many ways to do this, right? We can I don't know, just enumerate them. There's like what, 3, 4, 1, 2, 3. Yeah, there's 4 different ways to do it, right? So we can just enumerate all 4 and then compute the sum for each one, and then sort of figure out which one is maximal, and then just return that. But it turns out, in general, if you try to brute force this, right, you can write like a recurrence relation that describes this. I would encourage you to like try this at home. Um, the recurrence relation ends up being a little bit weird to think about. But it ends up giving you something like uh, big O of e to the square root of n over n. Um, and so the point here is it's like roughly exponential, right? And so the number of possible ways of cutting the rod is grows very fast, right? So it quickly becomes very intractable just to enumerate every possible sequence of cuts and just figure out which one is the best one through that. Um, okay, so we've laid out a problem. Hopefully that makes sense to people. If it doesn't, please let me know. Um, and I've sort of like tried to convince you that like a brute force solution of just like iterating through every possible answer and like checking which one's the best is kind of intractable. Are there any questions at this stage before we move into like interactively like having you all help me write an algorithm for this? All right. If there's no questions, let's move on. Okay. So, a recursive algorithm for solving the rod cutting problem. First of all, what's the base case, right? Divide and conquer, we need a base case and we need a recursive case where we break a problem into subproblems. So what's a good base case for this? What's like a length of rod that we trivially know how to optimally divide? Any thoughts? A single unit. Perfect. Yes. A 1 foot rod is indivisible, right? We can't do fractions of a foot. Yeah, a rod of length one. So if n equals one, then there's no other option, right? We have to sell it as it is, and so it's sort of trivial. We just kind of return that. Okay, that's a good enough base case. What are our subproblems? How do we take a rod of length n and think about uh, subdividing it? How do we turn the problem of dividing a rod of length n into a problem of like dividing a smaller rod? Any thoughts on this one? Division at every foot. Essentially, yeah, right. So if we fix one cut, like if we pick one place to cut it at, then we have a smaller rod that we can subdivide, right? We can choose we can like iterate over every possible place that we could cut, and then try to make a cut there, and then try to like recursively subdivide everything that remains, right? And in particular, an optimal subdivision of a rod necessarily restricts to an optimal subdivision of the union of some of its pieces, right? Like if I've optimally subdivided a rod of length n into a bunch of smaller pieces, I take some of those pieces and I glue them back together. I've necessarily the best possible way to subdivide those is the way that I'd already divided them. Because if there was a better possible way to subdivide them, then I could have just done that, and then that would have given me something better for my entire rod, right? Um, and so we have this like optimal substructure, right? In the sense that we can be sure that if we compute the optimal division of like something of size n minus k, then we then we get something that's optimal for size n, right? Um, Hopefully that kind of makes sense. At each foot in one half of the rod because of symmetry. Um, I guess yeah. Actually, I guess that's true. Yeah. Um, you could you could just go up to half of the rod. That works. Um, all right. Attendance poll for today. how many distinct subproblems are there here? And how does this compare to the complexity of this recursive algorithm? Right, so I'll leave this up for a minute. Feel free to shout out the answer. Uh, I guess first of all, how many subproblems do we have? Roughly in a big O like asymptotic sense. Have we gone over how we're fixing that one cut? So the idea is if we've somehow magically fixed one cut, then we have a smaller rod. And so for now, we can just kind of like loop through every possible one cut that we can fix, right? So this is just an algorithm that's guaranteed to find us a solution. It doesn't necessarily have to be that's guaranteed to find like the optimal solution. It doesn't have to be particularly efficient at this stage. That's a good question though. Any other questions before we move on? Okay, let's try implementing it. Gonna stop my share for a second, and then so share this. Okay, is this visible? Okay. So I cheated a little bit and implemented this last night, but we're gonna pretend I didn't, and we're gonna create a new file for this as soon as this decides to finish connecting. Here we go. New file. Oh, come on. There we go. All right. So, um, for starters, let's maybe write down an array of prices. And I'm just going to use the ones from the book. So 1, 5, 8, 9, 10, 17, 17, 20, 24, 30. And then I'm going to put a 0 here because we want it to be 0 indexed. And then the price for a rod of size 0 should just be 0. Okay. And let's write a recursive function that takes, let's see, int best price. It'll take an array of prices, and it'll take an integer length. Let me zoom in a little bit. Can everyone see, um, like, is this readable? Or do I need to change the font size or the colors or anything like that to make it more visible? Or is this good? All right, I'm gonna assume it's good. Okay, so very readable. Yes, great, thank you. All right, so we had a base case, right? What was the base case? 1 foot rod. Yes, great. So if length equals one, we return, we just directly return it, right? It also turns out if we somehow end up with a 0 foot rod, we should return that as well, right? I don't trust myself to not make an off by one error that makes this impossible to reach. So we're just going to keep that there. Okay, so here's our base case, right? And then for our recursive case, do you remember what we did? So we had to fix an initial cut, right? So we can maybe loop through all possible initial cuts, right? What should the bounds of this loop be? Okay, and maybe we can start at one. It doesn't really make sense to start at zero because that would be like not changing the rod at all. Okay. Um, and so given a cut, what does my recursive call look like? So I assume I make a recursive call, right? What do I pass in here? Or let's say like given some fixed cut here, how do I calculate the best possible price that I can get given that I'm making that particular cut? Actually, I don't think we want to go to length over two because this is fixing one cut, right? And so if we have something like a rod of length six, this would never give us like a sub piece of length four, even if that turned out to be optimal, because we would cut the two, but then we would have four, and then we couldn't take the whole four, right? So I think we do want this to be less than or equal to length. Right. So what's the price of the piece that we've already cut that we're guaranteed to have in our total thing? That's just going to be prices at cut, right? Plus, and we can just assume that our best price function is going to give us the right price for it's the same array of prices, but then we're going to look at length minus cut, right? So this is the best that we can do if we fix cut, right? So maybe I can start by saying int best equals negative int max. And I think I need to include limits.h for this. And then I can say uh, if price is better than best, then best equals price, right? Does this make sense? And then just return price or return best, I guess, right? So in the base case, if I've got something indivisible, I just return that. Otherwise, I loop over every possible way to cut it. And for a particular cut, I look at the price of that piece of rod that I've fixed that I know for a fact I'm going to have, and then I have the rest of the rod, which has length minus cut because I've already taken something out, and then I just like recurse on that. And so at some point, because the parameter that I'm or the argument that I'm passing for length is decreasing, at some point it's going to hit either zero or one, and so we're gonna terminate, right? So maybe I can um, we know that for four, right? this was the example that we had in the slides. And so we know that if we pass in 4 as the length, we know that the answer should be 10. Right? So maybe we can. Nope. Oh, and of course I need to import standard IO. Okay. And it gives us 10. All right. This is good, right? This is not a complete test case, but it's kind of good that it gives us the right answer for one thing, right? Um, what do we expect the complexity of this thing to look like? Can we kind of write down a recurrence relation for the complexity? So let's try to do that together. This is also maybe good practice for like a homework problem or something. Okay, so I want to write down some recursive formula for T of n, where n is the length of the rod, right? N is this parameter here. Um, and this is going to be a recurrence relation, right? Because we don't have a closed form for it yet. But what do we expect? Um, well, I guess first of all, what are our base cases for the recurrence? And what can we say in those cases? Any thoughts? Oh, one. Yeah. So the um yeah, right, exactly. So for the base case being like T of 0 or T of 1, you can expect T of 0 to be O of 1. You can expect T of 1 to be O of 1, right? And then for some other T of n, what can we expect this to look like? If I'm not in one of the base cases, right? But I'm in the recursive case, right? What's the complexity of this for loop? Any thoughts? How many times does this for loop run? The for loop runs O of n times, yeah. But what's the complexity of one iteration of the for loop? What am I doing in one iteration? right? I have something that looks constant here, and I have something that looks constant here with this addition. But yeah, we're calling the recursive function again, right? So maybe we can say, well, I'm going to write this as a sum because I think we're going to need to care about the iteration that we're on. So k equals 1 to n of, and I'll say O of 1 plus, if I'm calling the recursive function again, um, I can think of that complexity wise as just like plugging in my recurrence relation again, right? So I can think of this as like t of, and then what's the size for the recursive call? Like what do I plug in here? N minus k. Great, thank you. I plug in t of n minus k. Okay, yeah. So this is our recurrence relation, right? T of 0 is constant, T of 1 is constant, T of n is the sum from k equals 1 to n of a constant plus T of n minus k, right? We can pull this O of 1 out because it's the same every time, and so we can maybe instead write T of n equals big O of n plus the sum of T of n minus k as k goes from 1 to n. Okay, so this is, well, first of all, can we use the master theorem here to like get a closed form for this? And some votes, yes or no? No, because it's not divided. Perfect, thank you. Yes, that's correct, right? This here is not like T of n over something, right? So we can't use the master theorem. Um, but if we were to try to like guess what the complexity of this thing looks like, we've got a bunch of like recursive calls here, and so this is going to make it something exponential, right? Like we've got a bunch of recursive calls, and the depth here is going to be linear, so it's gonna look something vaguely exponential, right? Of course, the actual like parameter here changes, so it's not going to be quite like the n to the n thing or whatever. But yeah, it turns out that this ends up just computing this just like obviously goes through every possible cut. Yeah, exponential like 2 to the n. I think it ends up being something again like big O of e to the square root of n divided by n is the number of ways to like cut this. If you actually no, this one is literally 2 to the n because if you think about like uh a rod of some given length, right? This one will try every possible way of cutting it. In particular, it'll look at like it'll treat 1 comma 3 and 3 comma 1 as two different cuts, which means that at every point we've got the choice of whether or not to cut it, which means that we've got 2 to the n possible cuts, or maybe 2 to the n minus 1 is what I want to say. Yeah, 2 to the n minus 1, which is big O of 2 to the n. Yeah. Okay. So this is an algorithm that works, but it doesn't, it computes the correct answer. It doesn't compute it as efficiently as we would like, right? So, oh, I'm gonna clear my annotations and then here. Okay, there we go. All right. So, how can we do better? Actually, maybe first of all, let's try like counting how many calls we make to this function, right? So just so we can, um, well, yeah. Right, so I'll initialize calls to 0, and then I'll increment calls here, and then we'll just print the total number of calls that we made. So for a rod of size 4, we make 12 total calls. For a rod of size 10, we make 768 total calls, right? So this grows pretty fast. Um, yeah, okay. me go back to my slides and we can talk about uh, in general ways to make this better. Okay, so first of all, um, we have we have an algorithm that visits an exponential number of cases, right? We decided that it was something like 2 to the n. Actually, in this case, our algorithm was literally 2 to the n. How many can we try to figure out what the like let's try to like characterize how much extra work this is doing, right? How many distinct sub problems are there? How many distinct like inputs are there to this function? It depends on the length, right? Like the optimal answer is dependent on, well, obviously the prices, but the prices stay fixed across all the calls. So the parameter that changes is the length. And there's for a length of n, there's n possible like sub problems that we could be visiting, right? And so we're doing 2 to the n work, but really there's only O of n things to be thinking about, right? So in particular, we're recomputing the optimal subdivision for a smaller rod multiple times, right? If we've got a rod of size 4, then uh, every time we cut, like if we cut it for 1, we have to recompute it for. If we cut it for 1 and then cut it for 1, we have to recompute it for 2. If we cut it for 2, we have to compute it for 2. Like every time we do this, we have to compute 2 multiple times, right? Like every sort of smaller rod has to get recomputed. Um, and so this is a good sign that we can use some kind of dynamic programming. Um, and in general, there's like two main ways that we can apply this, right? So there's a top-down and a bottom-up. So the top-down approach, I think, is just easier to implement, right? It's easier to think about. And most of the time, if this works for you, if this like solves your problem, this is maybe just what you want to do, right? So the top-down approach is called memoization. This is not a typo. It's not memorization. It's memoization. Um, where basically we cache the optimal solutions and then use the cached solution instead of recomputing it, right? Um, so I don't know. I think maybe we've talked about this before, but the idea here is like we don't expect the optimal subdivision for a rod of length 12 to change at any point, right? So once we've computed it, we can just store it somewhere and we can just remember it and then we don't have to recompute it, right? And so as long as we have an efficient way of looking up a value that we've computed in the past, we can uh, we can turn like further subsequent calls uh, of this function on that particular input into constant time instead of being exponential time, right? And so that takes off a whole bunch of extra calls that we would be making, and it turns the whole thing into something much nicer. Um, that's the idea of memoization. We'll try actually re-implementing this with memoization. And so hopefully that'll give like a more concrete idea of how it works. But from a theoretical perspective, does this make sense to people? Cool. Okay, awesome. So that's top down, right? So right, top down is great because we take the function we already have and we just add a little bit of code to it to like save the output once we've computed it, and then before doing all of the computation, check to see if the output is one that we've already saved, and if it is, just read that instead of recomputing the whole thing, right? Very easy. Um, Bottom up is a little bit more powerful, but it's a little bit harder, right? So the idea of bottom up is instead of writing this as a recursive function, we rearrange all of our subproblems and make sure that we solve all the smaller ones first and then use them to like incrementally build up solutions to larger subproblems, right? So with the bottom up approach, instead of starting by asking the algorithm to compute the best possible cut for or the best possible subdivision for like n equals 4, right? We would say, okay, we know what it looks like for n equals 1, so let's just write that down. And then because we know what it looks like for n equals 1, we know how to figure out what it looks like for n equals 2. So we'll write that down. And because we know 1 and 2, we can figure out 3. So we'll write that down. Because we know 1, 2, and 3, we can figure out what it looks like for 4. So we'll write that down and just kind of like build this up incrementally, right? Um, so this is a different approach. The function is going to look different. The algorithm is going to look different, but we're not going to have recursion. We're not going to have caching going on or anything like that. In particular, this means we won't necessarily. Well, I guess we do use auxiliary space, but we'll sort of see that this has like a nice side effect of sort of telling us what the best subdivision is. Anyway, back to the live coding screen. I guess before I do that, uh, top down and bottom up. Does this make sense? I know I kind of asked about top down already, but like what we're trying to do on on the live coding screen, is everyone on board? Cool. Okay. What's up? And share. All right, great. So let's start by memoizing, right? We'll say maybe like uh, um, okay. So for starters, we can maybe just take the same code as before, but now we want to add an extra parameter for we want to add an extra parameter for like the saved the cache that we've already computed, right? Maybe I'll add an int array for cache, right? Um, and let's go ahead and initialize this to just a bunch of negative ones. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Okay. So first thing we can do is uh, actually, what is the first thing we should do here? If we're memorizing this function, right? Let's maybe go here, right? So here I want to cache the result, right? We can say cache at length equals best. Does that make sense? So I'm storing in this array that I'm going to pass in. I'm going to store the the optimal cut that we've computed, or the like optimal price that we've computed for this particular length once we've computed it, right? What else do I need to change about this function? There's a couple things. So I'm populating the cache here. Yes, exactly. We need to retrieve from it. So maybe I'll put this up here, right? We can say if cache at length is not equal to -1, because -1 is sort of our like sentinel value. Uh, then what should we do in this case? What do I return here? Let's return the cached value, right? Does that make sense? All right, there's one other thing that's missing. Or there's one other like change that I need to make. Any ideas?
Change the name like of best price in the for loop.
Yes, exactly. Thank you. So I make it best priced memoized, and then I pass in the cache, right? So now, um, if I let's open this up. Yeah, okay. So the price we computed before for 10 was 30, and it took 768 calls. So if I use the memoized version now, oh, then I'll give it my empty cache. It gives me 30, but now I'm using way fewer calls, right? 55 instead of 768. And so I hope this is sort of convincing that like just doing this little bit of work, right? In a problem where we have like a relatively small number of unique subproblems or like unique parameter sets that we're passing into our recursive function, we can pretty easily turn the complexity of this from something exponential into something linear, right? In fact, if we try to analyze the complexity here, it gets a little bit harder to do because now we have to like our recurrence relation has to like reason about whether this thing is going to be cached or not, right? So whether it's going to be constant time or whether it's going to be exponential. Um, but it turns out if you just sort of convince yourself that like every every element in the cache or every like value of length, every distinct value of length is only going to hit this stuff once. And otherwise it's just going to have a constant time associated with it. Then something like 10 is only going to visit each number from 1 to 10 one time. And so it's going to look like O of n instead of O of n squared, right? Um, okay, cool. So that's our top-down approach. In the what is it, 6 minutes remaining, maybe we can start doing some bottom up. Okay, so okay, so, all right. So the trick with the bottom up approach, as I mentioned, I'm kind of using this book as a reference in case I forget what it looks like. But the idea is we compute things in the order that we know they're going to need to be computed anyways, right? So we can say like int best cuts equals, or maybe I'll start with like best cuts. Um, okay, I'll include standard lib for this. Right, right. The correct order to compute these in is just increasing order of size, right? Because for something of length n, I need to know everything from 1 to n minus 1, right? To be able to do this optimally. Um, okay, so uh, okay for actually I'll make this length plus 1 because we need a 0 at the end, right? And then I'll set best cuts at 0 to be 0. Okay, so For a cut of length I can start by saying, right, same thing that I've done here, except now instead of calling best price memoized, I'm just going to look up the cut that I had, right? So now I can say for int cut equals 1, cut is less than or equal to this time I, and then cut plus plus. If and then the price, so we'll say int price equals, what do we say? It's going to be prices at cut plus best cuts. This is what, length minus cut, right? Yep. And then if price is better than best, then best equals price. All right. And then we say best cuts at I equals best, right? So instead of doing a bunch of recursive calls here and like saving things in a cache and all of that, I'm just remembering the I'm just remembering all of the previous calls and I'm just making them in the right order, right? And so now this is explicitly O of n squared. Actually, this should also be O of n squared because it's doing roughly the same thing. But yeah, this is now like explicitly what it is, right? It's like this goes from 1 to length, this goes from 1 to n or 1 to I, and so it's like n times n minus 1 over 2 or whatever that is. And yeah, so it's something like n squared. And then I can just return, or maybe I can say like int answer equals best cuts at length, and then free best cuts that I'm not leaking memory. I can return answer. Okay, so now if I replace memoized with bottom up, I don't need a cache anymore. And I can see, well, what did I do wrong here? I guess I should start by saying like, start at 2. Nope. What did I do wrong here? O of n squared, not O of 2 to the n. Well, this one, yeah, this one is going to be n squared, right? Because we've got 2 nested for loops. Our original thing was something like 2 to the n because we were making a bunch of recursive calls. Try this for 4. Oh yeah, I guess we're not like actually counting the number of calls. So price 11. Okay, so clearly it's a problem with that. Well, okay, it's 9:40. I'm gonna let you all go. Post I'll post the code for this. And then maybe spend some time, take a look at it, and think about it. Uh, all right, great. I'll also open the submission for the attendance poll. All right. Happy Thursday, everyone. Yeah, the attendance poll question was, can you characterize the number of sub problems and how does that compare to the complexity of the recursive algorithm? I'll stop the recording.